Hello, dear participants of the virtual ICM 22. My name is Thomas Schick from Göttingen. I'm moderator of today's section here. This time the sections Dynamics, Geometry, and Topology are joined, and I'm happy to announce David Fisher, Distinguished Professor from Indiana University of Bloomington, who will tell us about rigidity and invariant measures beyond homogeneous dynamics. David is traveling, so we will see a recorded talk, which I now think will start. Let's go.
It's a great pleasure to both be speaking at the ICM and to be speaking here live in Jerusalem. I will just point to the one thing on my slides that acknowledges the horrible events that have brought us to being here rather than in St. Petersburg. And I really can't say anything in even the allotted 45 minutes about that tragedy, so I'm going to just leave it at that. On the mathematics, what I want to do today, which maybe is too much, but I want to try and explain to you what is sort of a philosophical new way to approach proving rigidity theorems that's inspired in some sense by uses of homogeneous dynamics and number theory. And the first thing I'm going to do is start by starting from more classical things in rigidity theory and tell you something about them. And in particular, if you take one thing from this talk, I'm going to explain a way in which you can begin the proof of Margulis Superrigidity theorem that isn't really in the literature and is the simplest way to start. So I'll tell you why it's not in the literature as we go. So in this moment, G is a simple Lie group, which it will be throughout the talk. Right now, the real rank of the Lie group is at least 2. So for example, S ln R, where n is greater than 2. And then we'll be interested in gamma in G, a lattice. And for that, you can take the example to be S ln Z throughout this discussion if you don't know how these things work. So you could think of this about S ln Z and S ln R for n at least 3. And then the superrigidity theorem, which I state here, says that, if I look at any homomorphism from gamma into G ln C, and then I make some assumptions about it. I assume that it doesn't have bounded image, and I make some assumption about its Zariski closure. Then what happens is that essentially the representation extends. And so if you don't know what Zariski closure is and you're not used to thinking about unbounded, you should just think of this as a criterion that's quite general for when a representation of a discrete group gamma extends to its sort of continuous envelope G. And I want to tell you how to think about proving this. And so somehow what we're going to do, and I don't want to talk about this in detail, is we're going to pick a good representation of this Zariski closure H on a vector field V, on a vector space V, that defines an action of gamma on this vector space V. If you just want to think of it as Cn and assume I started with a particularly nice representation in the beginning, that's fine. Just have some representation of gamma on this vector space V, and with that we define a flat projective space of V bundle over G mod gamma with a left G action by this very standard construction. What am I doing here? I'm taking an element of, here's the space of my flat bundle. I get a point in G that's really up to some action by gamma. I get a point in the projective space of V, so I have these two equivalence classes. I can act on these two equivalence classes, one on the left by G prime and on the right by gamma here, so I have to put an inverse, and then I act on the fiber by rho gamma of V. And this is sort of a standard construction that goes back to Mackey of an induced action. And so I have this action on this flat bundle of this group G. And it's a nice action. And what do I do? I'm going to give you the first steps in the proof of this, and this is really following, in some sense, Zimmer, and not really Margulis. It's also maybe following a little bit Zimmer, following Furstenberg, following Margulis. So we take P and G, the minimal parabolic, which is just a set of upper triangular matrices if you're thinking of S ln R. And we take this group, and the key step is really that there is a P invariant measure mu on this bundle, and in fact that measure can be chosen to project down to Haar measure on G mod gamma. This bundle has a map to G mod gamma just by forgetting the second coordinate. When I call it a flat bundle, I think of it as coming automatically with a projection to the base. And so why does this measure exist? In this case, it's just amenability. You can just start with any measure on the big space, and you can average it over P, and you get an invariant measure. If you start with a measure on the big space that projects to our measure, the averaging will keep that. And so this is really the first step in the proof of Margulis' superrigidity theorem if you follow Zimmer, although you can't find this in Zimmer's papers written this way. And it really just uses amenability of P. And what this does from another point of view is it builds a gamma equivariant measurable map from G mod P to measures on P of V. I just think of, if I think of a point in this bundle, on the fiber over that bundle I have a measure, and I can, the fact that the measure is invariant under P means it's actually a map from G mod P, and I, lift out the gamma action and think of it as a gamma equivariant map. And this map was discovered earlier by Hillel Furstenberg, but he built this map by a very different method using random walks, and I think it's, if you know that proof, this proof is simpler, and really kind of not in the literature in a clear way anywhere that I know of. It's implicit in Zimmer's work. And so, we have this action on measures on this projective variety of gamma, and we have this map from measures on this other variety to measures on this one, and that's not the greatest thing in the world. And then I just want to tell you that there's sort of a standard step here that uses ergodic theoretic properties of the action on G mod P and rigidity of measures on algebraic varieties to show that you can actually realize this map somehow as a map from G mod P to some other algebraic variety. And this again, in sort of the form I'm thinking of this is due to Zimmer using ideas of Furstenberg. There is a newer way of thinking about this that works more generally due to Bader, Duchenne, and Lecoureux. And so, this is the way you start Margulis' theorem. It is true that I'm now going to omit the hard part. The hard part is proving something about this map that proves a rigidity theorem. But that's not the part of the proof I'm interested in today, so we're going to skip that part. I will say that part of the proof has also been simplified dramatically recently by Bader and Furman, but other than that, I'm not going to talk about that. So I now want to talk about a way in which this has been the way in which Zimmer thought about this that sort of hid the easy argument I just sketched for you. He thought about this, he wanted to think about a general action of some arbitrary group on a measure space X mu, and he defined something called amenability for an action, generalizing amenability for a group. And amenability for an action is exactly, more or less, it's sort of a generalization of the existence of this map. It says every time I have D acting on some compact space Y, I get a D equivariant map from X to measures on Y. And this really generalizes that map from G mod P to measures on the projective space in a relatively straightforward way. And this, is an interesting definition. It's been used for a million things. It's very useful for proving rigidity theorems in lots of contexts. It turns out not to be the right generalization for proving the kinds of theorems I'm interested in today. And I think part of why they were resistant to being proved is because we went in one direction when for certain purposes we should have gone in a different one. One thing that's interesting here in terms of just how the variant works is if a group has a measure preserving amenable action, then the group is amenable. And as I talk about the generalization, you can notice that this makes this definition actually formally useless for some of the things I'm going to do. It's not formally useless for all of them, but for some of the things I'm going to do, it's actually formally useless. It can't be applied. So now we're going to try and head in some other direction. And I'm going to try and describe for you a philosophy of proof. And this is something that I decided to do in this talk, even though I think it's hard to do and maybe dangerous to do because it's going to be a little vague. And I hope you stick with me. The idea is to describe a philosophy of proof. And then the rest of the talk is describing two places in which the philosophy is implemented to see practically what's going on. So here's a philosophy of proving. And it's still somewhat ad hoc. I'm not as clever as Zimmer, so I can't give you a definition that captures my philosophy like the definition of amenable actions. So I'm just going to think of some subgroup of my group G, and assume gamma acts on some compact space. And I'm just going to tell you there are lots of problems where these things can arise. And the key step in the philosophy is always going to be finding some d-invariant measure on this product space built in exactly the same way as before. And this measure should project a Haar measure on G mod gamma to be useful. And this is just, okay, we'd like to be able to do this. And I'll just say that this is the same as finding a gamma equivariant measurable map from G mod this other group D to measures on Y, but it turns out that to actually find it, it's more useful to think of it as a measure than a measurable map, which is why I emphasize this particular way of thinking about the proof of Margulis' theorem, is because that's what we actually think of when we're generalizing, is to find the object you want, you have to think of it as a measure. And what you can do is you can think of mu and d as being constructed to encode some data about some problem you think about. And now this is where I say, this shouldn't seem that strange, especially to some members of this audience, because if you're using homogeneous dynamics to prove something about number theory, or if you're using dynamics to prove something about number theory, often the strategy is you start with some problem, you realize there's some group involved, and that you can build some action of the group and some measure that tells you how to solve your problem as long as you know something about the action of the group in the measure. And so it's the same kind of philosophy, but being applied in a different setting to prove theorems about rigidity of group actions. And in practice, the measure mu that I'm going to build is always going to be a weak star limit of a sequence of measures, and the sequence of measures are going to be witnessing some phenomenon. And again, that's very familiar in applications of homogeneous dynamics to number theory. So this is borrowing an idea that's been used robustly in one area and moving it to another one. And the rest of the talk is, as I said before, it's just two very different examples of the philosophy in practice. And let's start by trying to set up the first one. So for the first one, I have to define what arithmetic is. So we say my lattice gamma in G is arithmetic. If G can be realized as some kind of algebraic group over a field, which is a number field, and gamma is commensurable to G of the integer points. And really, if you don't know this definition, I'm probably not helping you very much, and you should just think of, the integer points in your matrix group. Just think of your group as a matrix group, think of its integer points. This is some slightly fancier variant on doing that in fact captures many of the important and interesting examples of these objects. And in fact, a corollary of Margulis' superrigidity theorem is his arithmeticity theorem that says when G is simple and higher rank, and gamma in G is a lattice, then gamma is in fact arithmetic. So for these higher rank groups, this slight generalization of the integer points is exactly all you need to capture all of the lattices. And not higher rank, that's not true, and it will matter for us. This arithmeticity theorem was, and versions of the superrigidity theorem were extended to these two rank 1 groups by Corlett and Gromov-Shane, but that's fairly far from my topic here, so I'm going to skip it. And I'm also just going to mention, I don't think I will read it because I think I'm already running behind my time, but there is a variant on this of Margulis's that does work for the remaining Lie groups and gives you some kind of criteria in terms of commensurators for when a lattice is arithmetic. And so now I want to give you, why this is here is because I want to give you a variant on it. I want to give you a different criteria for when a lattice is arithmetic. And to give you this criterion, I have to now think, instead of about groups about spaces, I have to think geometrically for a while. So I'm going to think of X tilde as an irreducible symmetric space of non-compact type and not Euclidean. If you want to think about real hyperbolic space in dimension n, please do so. It'll say that again on the slide later. And then I want to think about some manifold that's X tilde mod gamma and has finite volume, so it's a finite volume locally symmetric space. And then the theorem that's due to myself and Botter and Miller and Stover in 2020 says, if this X contains finitely many maximal proper closed totally geodesic submanifolds of dimension at least 2, then gamma is arithmetic. And so, closed and totally geodesic, I'm going to take for granted that we know what those mean. The fact that they're of dimension at least 2 is important. Dimension 1 is just geodesics. I don't want to think about geodesics. The theorem is not true for geodesics. And maximal just means the only thing maximal ever means, which is it's the biggest one, it's not contained in another one. So maximal is not contained in another proper closed, totally geodesic submanifold. And really here you can think that this symmetric space is either hyperbolic space or complex hyperbolic space, because the theorem is only new there. All the other lattices are arithmetic anyway. So it only can have content there. Our proof really only works in these 2 examples. You might be able to extend the proof more generally, but A, you don't want to, and B, it seems difficult. And really, maybe the better way to think about this is that it's a finiteness theorem. It says if you take a lattice that isn't arithmetic in one of these 2 things, then there's some sort of finiteness of maximal closed, totally geodesic submanifolds that maybe resembles very vaguely the finiteness of periodic orbits that we saw in Dujardin's lecture. And again, in case someone is here or listening or watching later and doesn't know, the connection back to what I was saying before is, this symmetric space, of course, its isometry group is G, which is in fact, I've set things up so I should say a simple Lie group, and gamma in G is a lattice. So we're in a sort of similar setting to Margulis' theorem, except for the fact that we're in real and complex hyperbolic spaces, so it's not a higher rank group, it's a rank 1 group. And now I want to say something about the history of this question, and I'll say it relatively briefly. The question was raised by Reed and McMullen in around the mid-2000s. Nothing was known about it for a very long time, and then the brief history of actual results about it is 3 years long, and was a strange experience just because I wrote 3 papers with a team of co-authors that changed once. I should just nod to Jean Lafont for being involved in the first project on this that didn't use the techniques I'm talking about here. And in each case, there was sort of a competing paper that came out at or around the same time. And I will say, I don't like mathematics being quite this competitive. It was quite nerve-wracking to have competing papers coming out at almost exactly the same time you were producing yours. It was invigorating, but I don't want to do it again. And the other thing I'll say is that totally geodesic manifolds have played a key role in hyperbolic geometry for a very long time. And the thing that's surprising to me in retrospect, now having learned a lot about this subject, is that it's very strange that this question was asked by Reed and McMullen in the 1970s and not by, say, Milson or Raghunathan in the 2000s, and not, say, by Milson and Raghunathan in the 1970s, or by Gromov and Piateski-Shapiro in the 1980s. There are things that were being done at various points in history that make this a natural question, where I'm surprised no one noticed it for quite as long as no one noticed it. So I want to now talk to you about why this is a dynamical theorem and not a geometric theorem, and how I'm going to play my game that I promised you I was going to play of finding invariant measures for the action of some group on some bundle over some G mod gamma. So the main point here is how do we find dynamics? Well, the frame bundle of real hyperbolic space is the same as its isometry group, which is the group SON1. So the frame bundle of the quotient manifold is just G mod gamma. And then it's relatively easy to write down a proof, although maybe more painful than I thought initially, that in X, closed totally geodesic submanifolds of dimension K come from, well, I should have the word certain here, orbit closures of this subgroup. If I want a closed geodesic submanifold of dimension K, I should look at either closed orbits or really more generally orbit closures of the group SOK1 sitting in the group SON1 acting on G mod gamma. This really is exactly the same thing. It's somehow, writing down a complete and correct proof of this is a little tedious and annoying, but it should be, it's geometrically obvious, but annoying to prove completely. And the one thing to notice is that this group SO11 is just the diagonal matrices, and it gives the geodesics. So this is this somehow, the action of SON1 on this space G mod gamma is the familiar for many people geodesic flow, and we're just looking at sort of higher dimensional generalizations of the geodesic flow. And For complex hyperbolic space, life is a bit more complicated. I will say this very quickly. Somehow you end up with the group SOUN1, which is the isometry group here. It's not the bundle of all frames, it's the bundle of complex frames. And there are two kinds of totally geodesic surfaces. And so instead of just getting one family of groups that you have to study, you get two families of groups, but it's still a finite family of groups, and it's not, at the steps I'm going to talk about today, very different. It's technically a little more complicated, but not very different. And you're really studying orbit closures of W on G mod gamma. And so here's how you rephrase the theorem dynamically, is you say, let this W, W is always going to be one of these groups on these slides sitting in this G or that G. And you let W act on G mod gamma, and you call a W orbit closure maximal if it's not contained in a larger proper W orbit closure. And the theorem, really, by the same four authors, really says if there are infinitely many maximal W orbit closures in G mod gamma, then gamma is arithmetic. It's absolutely the same theorem. Maybe I should have stated this one first, but the motivation comes from geometry for this theorem. So that's the way we state it first and state it in the papers. And again, it's a sort of a finiteness result for non-arithmetic orbit closures. And somehow the key idea is if I have an orbit closure, my orbit closure always carries a W invariant measure. This is something that is elementary in homogeneous dynamics. And what I want to do is take those measures on the orbit closures, and I want to lift them to invariant measures on some projective bundle for some representations. And this is where things get very tricky to say explicitly, so I'm going to be vague, is that, in Margulis' setting, because you have an amenable group, everything works very generally and very softly. You don't need to know anything about your representations or what this bundle looks like. You just need a compact space and everything works. Here you have to do something finicky. You want to take these sort of obviously given invariant measures, nu I, on the orbit closures, and you want to lift them to the projective bundle using the structure of certain representations that you have to study to prove arithmeticity. And then you take these lifted measures and you take a weak star limit of them, and using work of Moses and Shaw that builds on work of Ratner and Donnie Margulis, so using a whole lot of homogeneous dynamics here, you see that the weak star limit of these measures project to Haar measure. And so what you do is, you pick your group W, and you start with some family of invariant measures. You lift them to some slightly odd space that's not homogeneous, and then you take a weak star limit, and you get, using some homogeneous dynamics on the base, a measure that projects to Haar. And I want to say something about the proofs, but not enough. And it will also contain a question about proofs that intrigues me and maybe not my co-authors as much. So the proof is via a superrigidity theorem. And the first step is, what we do is we take this invariant measure from the last slide, and we do the same thing I talked about before, and we turn it into an equivariant map from G now mod W, which is now a non-compact algebraic variety, to some other algebraic variety. And we now turn this into a problem of studying measurable maps between algebraic varieties, which is a subject in its own right, in which we use many techniques. And this map just again comes really, it's just disintegration of measures and some fairly standard yoga and a few other things. But it's not, there's not a lot of insight at this step in the proof that's new to us. And the second thing to do is you now study properties of these mappings to extend the representation. I'm going to tell you nothing about how we do that. I will tell you that the conclusion has a slightly weird reformulation when you're thinking about things from the point of view I'm thinking about them today, which is the conclusion has this, oops, I knew I was going to do that once. The conclusion is actually equivalent to the fact that this W invariant measure mu is G invariant. It's formally equivalent to that. It's not how the proof works. And so this, there should be a question mark at the end. This is a question I'd really like to know is there a proof? If I start with a W invariant measure and I end with a G invariant measure, I should be proving it by taking my measure and increasing the invariance of my measure. This too, especially when you're working with a proof that started out inspired by homogeneous dynamics and number theory, this is what you want the proof to look like. And it doesn't look like that. And I have no idea how to make it look like that. I did try for a while before we came up with the proof we came up with, but it doesn't, the proof we came up with works. And I want to add just one more comment on this part of the talk, which is that you can actually write down several characterizations of arithmeticity and superrigidity purely in terms of invariant measures for various subgroups of G acting on this projective bundle. And they are in the proceedings paper, connected to this talk. There are several characterizations of arithmeticity and superrigidity just in terms of things about measures. I was just kind of obsessed with that while writing the talk and writing the paper, and so there are some in there. I don't know if I found the right ones or the best ones or the most useful ones. It was more a proof of principle that you could characterize these things in terms of measures on this space. And in particular, it's a rather strange thing that non-arithmeticity can also be characterized by things on this space, and the characterizations are not what I expected. So now I want to flip the page, and flip the page completely and talk about, I promised you 2 instances of a philosophy, and that was one. And so now we flip the page and we talk about another instance of the same philosophy. This one actually came first, historically, and sort of motivated at least my thinking about the second one. Yeah, it just is less directly connected to Margulis' theorem, so I put it second in the slides. So now we're going to go back to the connection setting of Margulis superrigidity and be looking at a lattice gamma in the group S-ln-R, and I'm always going to assume n is greater than or equal to 3. You can put more general G's and gammas here, and maybe in Brown's talk, and he'll do that, or maybe he'll decide not to too. And then you let M be a compact manifold, and you take a homomorphism from gamma to diffeomorphisms of M. So this is a gamma action on some compact manifold M, and what then the theorem says is then if the dimension of M is less than n minus 1, then the image of this homomorphism is finite. There are no interesting actions in low dimensions. And the same thing is true 1 dimension higher if your action preserves a volume form, but we won't worry about that too much today. What I will say about this for different G's is if you put different G's here, the reason why I only do S-ln-R is because I have these, if it's S-ln-R, I get n minus 1. If I put a different G, I then have to tell you how to compute the numbers that go in those places, and that takes too long for a 45-minute talk. Or, in fact, I'm not sure I've ever computed those numbers in a talk, or even explained those numbers in a talk. So the key ingredient in the proof is relating growth of derivatives to properties of invariant measures. And again, before I was working on before I was putting a projective space here, and gamma was acting on the projective space in some natural linear way, the construction didn't care. The construction, I can build a flat M bundle over G mod gamma, defined, where the bundle and the action on it are defined by exactly the same equation as before. I now realize that, this G should not have an equivalence class bracket around it. There's a typo in the slides. It was in the other place too. Hopefully it didn't devastate anyone's understanding of my talk. Somehow in the proof, it's essential to use algebraic structure of G and homogeneous dynamics on this base manifold G mod gamma. And so we have this theorem, and we have this use of homogeneous dynamics that's going to come up in its proof. But first I have to tell you something about this sentence. The key ingredient of the proof is relating derivatives to properties of invariant measures. And again, what I want to do is I want to find some subgroup of G and some invariant measure on this space that's going to encode some obstruction to solving the problem. And it's a little harder to do here, which is the other reason why this came second. Or maybe it's not harder to do. It felt harder to do as I was writing the slides. So now I need a definition that's a little technical. The definition says that if I have an action of gamma on a manifold M, and I want to assume that gamma is finitely generated, so I can talk about the lengths of elements of gamma, and gamma is acting on this compact manifold, then we say that the action has sub-exponential growth of derivatives if every time you give me an epsilon, I can give you back a c, so that if I look at the derivative of the action of gamma on x, and I take the sup over elements of m, so I look at the largest derivative this element gamma has on the manifold. That's bounded by my constant times e to the epsilon times the length of my word. So it's some sort of slow growth of derivatives. It's a uniformly slow growth of derivatives, and it's a growth of derivatives that's, it's essentially the formal negation of hyperbolicity in dynamics. It's the formal saying there's absolutely no hyperbolicity allowed in my dynamical system. That's more or less what it says. And there's then, why do we care about this? I'll tell you the second half of the proof first. That tells you why we care about this sub-exponential growth of derivatives. So we're going to let gamma have some property, which is called strong property T of Laforgue. The gammas we're going to care about will have that property. That'll be the next thing on the slide. We're going to let M be a compact manifold and assume we have an action that has this sub-exponential growth of derivatives. And then what we get out of that by an argument that's at least shorter than the other arguments in the paper is that gamma preserves a smooth Riemannian metric on M. It's a relatively short argument. It's not, we wouldn't have written the first half of the paper if we didn't know the second half was going to work. It's one of a paper that gets written that way. We knew this was going to finish the theorem before we spent all the time writing the other half of the theorem. And so why do I care about, I realized I didn't put this on the slides, why do I care about preserving a Riemannian metric? I care about preserving a Riemannian metric because once I do that, the answer's sort of known. Zimmer knew how to finish proving Zimmer's conjecture if there was an invariant Riemannian metric. When he made the conjecture, which I should have said earlier in 1983, and in fact I should have said this more, right? The title of the slide was Zimmer's conjecture, and I didn't bother to say out loud. This theorem was conjectured by Zimmer in 1983. There's a lot of previous work on it. Maybe because the work on it hasn't been as active recently before we proved it, I didn't feel obligated to put it on the slides. But many people have partial results towards this theorem over many years, and I should have put some of that on the slides. I was worried that would force me to go over time, and now I'm worried that I'm going to actually go under time by a lot. We'll see what happens. So now I have this thing that says if I have strong property T of Laforgue, then I preserve a smooth Riemannian metric, and what I just told you was that Zimmer now tells me I'm done, and it's an easy argument that tells me I'm done here. This is not hard. And then there's this theorem of Laforgue in the case of co-compact lattices, and in de La Salle in the case of non-co-compact lattices, that higher rank lattices have strong property T. And in some sense, we wrote a paper proving our theorem about co-compact lattices, and then we're working on generalizing it to non-co-compact lattices, and de La Salle proved the version of this for non-co-compact lattices sort of on commission. I asked him if it was true. He thought about it. We talked about it for a while, and not that long later, he came back with a proof that's a very beautiful proof that has many novel ideas in it. Turns out if you tell someone, if you prove this, there's an application that's really great, then something that the field has been stuck on for a while, people get creative about. So now I want to talk about my general philosophy and measures as obstructions. So, and for this, I'm really going to be talking about co-compact lattices. Maybe I'll say a word about non-co-compact lattices a little bit later. I can write my group in this Cartan decomposition. I can write it as KAK, where the important part here is the group K is compact. In the case of S ln R, A is just the diagonal matrices, K is just SON. And if you take the Cartan decomposition and you do an argument that's really not too hard, it's a few pages, what it tells you is that if gamma is mapping into diffeomorphisms of M in the setting of our theorem, then either my action has sub-exponential growth of derivatives, or there is some A invariant measure mu on G cross M mod gamma with positive first Lyapunov exponent for some A and A. So I'm saying, I found some nice measure, and I'm actually hiding a step here. Really, you get a little A invariant measure, and then I'm averaging it over big A to make it big A invariant. So I'm already hiding a step of averaging in this statement. And why do we care about this lemma? Well, what Zimmer's co-cycle superrigidity theorem that, why Zimmer made the conjecture in 1983 was because he proved something called co-cycle superrigidity, which is a little bit technical, so I didn't want to state it on the slides. And so I didn't state this little bit technical thing on the slides, but what the little bit technical thing tells us is if instead of an A invariant measure, I built you a G invariant measure, it couldn't have positive first Lyapunov exponent. So the game should be to take my A invariant measure and build for you a G invariant measure instead. And the other thing that's hiding in this statement that's relevant to my philosophy is that in my philosophy I was supposed to find a subgroup and a measure, and that measure was supposed to project a Haar measure on G mod gamma. And in this lemma, I'm not making that second claim. I'm not claiming the measure projects the Haar measure on G mod gamma. That turns out to be a lot of work in this context. And I'll talk about it soon. So this is a slightly worse starting point. And the one other thing I should say about this lemma is this lemma really is built. Again, I didn't do this on the slides because it looks too technical. What do? You take this definition and you negate it. If you negate this definition, you get a sequence of points seeing more and more exponential growth of derivatives for longer and longer orbit sequences. And you just write down what that means. And it gives you a sequence of finitely supported measures witnessing the exponential growth. And you take a weak star limit of these measures, and that's how you get this measure mu on G cross M mod gamma, and it's some sort of it's the ergodic theorem plus the chain rule plus the negation of the definition. It's not a terribly hard argument, but it is this measure is built as a weak star limit of measures witnessing some obstruction to what you want to have be true, and that's something I promised you about my philosophy. And now, well, the goal is to, this begins to seem a lot more like homogeneous dynamics. The goal is to average to improve invariance, but we have to do that while retaining this positivity of the first Lyapunov exponent, right? If I get to a G action, to a G invariant measure with positive first Lyapunov exponent, I get a contradiction and I win, because the contradiction tells me that I have sub-exponential growth of derivatives, and then I win by the last slide. And so now the goal is to average to improve invariance while retaining positive first Lyapunov exponent. And the other thing that I will say is that for non-uniform lattices, the lemma becomes much more difficult. And in fact, it becomes most of the work. And the issue is the same issue that one always encounters. What does non-uniform lattice means? It means this space G mod gamma is not compact. I didn't tell you why this wasn't a problem for the other problem, but for the other problem, it's an easy problem. For this problem, it becomes, for the totally geodesic manifold problem, I might have a cusp. In that case, it's not a big deal. In this case, if I have a cusp, it's not a cusp, it's a higher rank cusp, so it's some kind of flare. And it's a very big deal to try and understand what happens there. The co-compact paper is about to appear. It's about 50 pages long. We wrote a paper that just did the case of S ln Z that's about 60 pages long, and we have a 100-page preprint that does the full thing. It's much, much harder. First thing that's going to happen is your finite measures that you're taking a limit of, they might drift out the cusp. And then even if you get these measures to stick in the thick part of the space and not drift off to infinity, the Lyapunov exponent might still fade off the cusp. There's something, and that's something that I don't know of any parallel to in homogeneous dynamics, is the kind of extra escape of Lyapunov exponent that we have to deal with here. I think it's really a problem that's intrinsic to certain kinds of rigidity theorems and not really natural in other contexts, but I don't know. There's some kind of other escape that we have to worry about that's harder to control than escape of math. And the other thing about this argument that I wanted to say that's a little bit weird, and definitely I also know of no other instance in which this occurs, is what we do is we factor the infinity of this higher rank manifold into the infinities of a bunch of rank 1 manifolds. And I don't know any place else in the literature where that occurs in a sort of dynamical argument about measures, right? There are places where that occurs. I mean, where we're sort of borrowing the proof of that is from a theorem of Lubatsky, Moses, and Raghunathan, but using that in a dynamical setting is something I've never seen before, and I'll admit here that it was not my suggestion, and I thought it was very unnatural. It turns out to be what works. Yeah, so now I'm no longer long on time because I've been blathering. So what do? The first step in what we do from now on is averaging so that the projection of the measure to G mod gamma is Haar. I want to put this back in the context of my general philosophy somehow by getting this projected measure to be Haar. And for this we use a tremendous amount of homogeneous dynamics. We use theorems of Rotner and Shaw on unipotent dynamics in the case where the lattice is uniform or co-compact. In the case where the lattice is non-uniform, we have to use, in addition to that, results of Kleinbach and Margulis on exponential mixing in the non-uniform cases, or at least some of the non-uniform cases. And there are a whole bunch of new ideas in the non-uniform cases, and I think I've tried twice in my life to talk about the non-uniform case. It's quite hard to talk about, and it does not belong in this 45-minute talk. And the other thing I'll say is that this step 1, and in fact, I didn't make this clear in the lemma. Neither the lemma nor step 1 uses the dimension bound. I said that I'm acting on a manifold of low dimension. You can get this far without using the dimension bound. I should go back and say the other place where the dimension bound comes in is to apply Zimmer's co-cycle superrigidity, you need the dimension bound. That won't give you a contradiction without the dimension bound, but otherwise building this measure doesn't use the dimension bound. So this measure exists in much broader contexts. Brown, Rodriguez, Hertz, and Wang have in fact used this measure for other things in other contexts. And then there's step 2, which is to show that the measure, once it projects to Haar measure on G mod gamma, is necessarily invariant under all of G, sort of miraculously. And this, it uses dimension bounds very strongly. And it's essentially built on entropy arguments, based on the deep work of Le Drapier-Young from the 80s that also has been used in homogeneous dynamics many times, and in many areas of dynamics many times. And in fact, this sort of a Le Drapier-Young idea, the Brown-Rodriguez-Hertz paper that Dujardin mentioned this morning also uses these ideas. And we also, if you're in the case that I just wrote on the board, this SLNR, you can get away with an argument just based on the actual paper of Le Drapier-Young. If you're looking at co-compact lattices and SLNR, you can get away with a cheap argument that just uses their work. And if you want to prove our most general and best theorems, you need a stronger result by Brown, Rodriguez, Hertz, and Wang that gets you the entropy estimates. That gets you sort of a stronger version of the entropy implies rigidity of the measures. And now I have a minute or two left, and I just want to go back. I should have put it again at the end of my slides if I was more organized and less nervous. But here again is this philosophy that I've given you 2 instances of. When you're trying to prove some rigidity theorem about a group action or a property of a group or a property of space on which a group acts, it might be a good idea to try and find some subgroup that encodes some information about your problem, and then find some space that encodes some information about your problem, and try and build an invariant measure for that group on this resulting suspension space that projects to Haar. And then analyzing this measure should be a way to start thinking about your problem and maybe solving it. And the last thing I'll say is that actually I put this in this context because that's where my own work exists. Another thing you can do that actually, in fact, has been done is instead of G mod gamma, you could put this moduli space of flat structures on Riemann surfaces that appeared in the talk of Chaika and Weiss, and you could try and do something very similar to this there. And in fact, there is a paper of Eskin, Philippe, and Wright that is very much doing that. And so this is actually, I put the philosophy in the G mod gamma context to have something to say and to be concrete, or at least more concrete than this vague slide seems. But it's actually, I think it's actually a much broader philosophy than that. And I think I will stop there.
Okay, yeah. Also, goodbye now to the virtual audience which has listened to the talk today. After recording, this ends our section. I remind you that there is a plenary talk in half an hour on the mathematics of machine learning. So I invite you to come, and I hope you enjoy the rest of the ICM, and I see you soon again. Bye.